I've been working with Nick to develop a Landsat quality band with TensorFlow and Earth Engine. And I'm going to walk through some of the work that we've been doing and highlight what we have. And I guess since this is, I generally like to keep these presentations very informal, but given that it's over the internet, maybe we can hold the questions till the end, and I'll be happy to walk through the questions. And Nick, you're probably going to have to help me with a lot of these questions too. Okay, so to get started, so why are we using deep learning for generating a quality bandmask? Well, when you look at current research for creating cloud masking, one, it's a really important step in remote sensing because clouds obviously affect the radiometric values that you're receiving from the Earth's surface to the sensor. And there's been a couple algorithms for Landsat that have been developed, and the current state-of-the-art algorithm is one called CFMask. And this uses some physically based decision trees, like if the pixel is cool, that's usually a cloud, or if it's really bright, it's a cloud. And then it uses some statistical aggregations from that decision tree to kind of refine that output. And so these physically based algorithms are really good because they have like physical basis on why they should work, but a lot of times there's these edge or boundary cases where you have values that are outside of what you have determined, and that can lead to erroneous cloud masks or shadow masks or what have you. And so if you see here on the right, here is just a quick example of kind of what I'm talking about, where you have this Landsat image, and this is obviously snow here, but what the cloud mask is picking up is a lot of clouds. So in this case, I think it's pretty sensitive to these thin clouds, but depending on how you classify clouds, it could go either way. And so when you're looking at these hand-labeled data sets, this CF mask only has about 70% agreement, which is really good for across the globe, but can we do better? And so there's been current research that has come out using deep learning for creating these quality control classes for Landsat. And basically, they show that they have a large improvement over CF mask, where the accuracy is around 95 to 97%. That's awesome. And so why are we doing this work? Some of these models, when you look at the architecture, they may not work well with how Earth Engine passes the data between Earth Engine and AI platform or vice versa. And so we want to be able to build a deep learning TensorFlow model for large-scale cloud quality masking on Earth Engine. And that's what we're going to talk about today. So how do we do that? First off, to do this, we need training data set. There's no deep learning process without a lot of training data set. Luckily, there is already some existing training data set. There's the Spatial Procedures for Automated Removal of Clouds and Shadows, or SPARCS. This is a really nice data set that this guy Hughes has created. He's actually working with, or has worked with, Robert Kennedy as a postdoc. And so this data set provides clouds, shadows, water, snow, ice, and clear pixels. And this is a great data set, although it doesn't cover all the cases of clouds, shadows, snow, and water. Again, we want to look at those edge and boundary cases as well. And so when you look at the data set, they don't cover a lot of very, very thin clouds. So we supplemented this data set with the cloud cover assessment validation data. That was used to help with the CF mask. And so to make this data set homogeneous with the SPARCS data set, we needed to provide some water and snow ice classes. And so we just used the unsupervised clustering algorithm to generate those. So that way we have these labeled data sets that have clouds, cloud shadows, water, snow, ice, and clear labels. And I'm providing scripts down here, so that way you can, this is a script to do the sampling. So if you click on it, you should be able to go and see what's going on. And so this is an actual example from the labeling where the points, and I'll talk about this a little bit later, or actually now, where the points are the center points of these chips that we're sampling. So we sampled 256 by 256 little image chips, and you see a lot of these dots and the sampling, and that's because we use what's called an oversampling technique, and this is the way to increase your samples by a large number. So deep learning models need a lot of training data, so we kind of did it this way, so that way we get different views of the image. So if you imagine this point here and these 2 points here, although they have, you know, more or less the same pixels, you're getting different looks at those pixels, and then you can also do some random flipping and rotation while you're training to help abstract these parameters that you're training for. And so these data sets were one-hot encoded, so that means each band in the image is either zeros or ones to classify whether it's cloud, no clouds, and then, or whatever class it is. And then these were, when we're exporting, we manually inspected each export to make sure that the hand-labeled data set that we're exporting was actually of high quality. So, you know, there are human errors associated with hand labeling data sets, but in this case, we wanted to make sure that everything was as high accuracy as possible. Okay, so next part, so now we have the training data set, now we want to have the model, right? So what kind of model did we actually use? So we used...
Sorry, Kel, apologies if I missed this. How many points or patches resulted from that previous training set?
I will have to look at it, but I think it's on the order of 13,000.
Okay, thank you.
Yeah, it's a good amount, and I have it all on cloud storage, and I can share, and probably we can look at it in detail if needed later on. Okay, so for the model architecture, we used a couple. We basically tested two model architectures. Everybody's probably familiar with this UNet that we tested. There's also something called a link net, which is basically a UNet. Instead of concatenating across, you're actually adding the data. So they're residual layers instead of concatenation layers. And basically, those provide you know, two different ways of upsampling. And so for the model backbone, so for the downsampling process, we used a model called VGG19. This is a pretty well-known model in the deep learning community. And basically, this is the model architecture here, where you have blocks of convolutions, and then at the end, max pooling. And so if we have these 256 by 256 images, basically at the bottom of this downsampling, we end up with an 8 by 8 image with 512 deep channels. Okay, and so that was talking about the downsampling. Now we need to talk about the upsampling. So there's a lot of ways you can kind of build upsampling. So we used a custom decoder block. And basically, this used a 2D convolutions, and at the end, we used the bilinear upsampling. You can use, typically, you can use the bilinear upsampling or transpose convolution 2Ds, which are you know, convolution 2Ds, but with different strides to kind of upsample the data set. In this case, we just use bilinear to reduce the number of actual parameters per for the model. And each convolution layer, so each layer here, has a what's called a he-normal initializer. So basically sampling from a normal distribution to initialize the model parameters before training. That helps increase training time. And then also an L2 regularization. And that's to help prevent these model parameters from overtraining. And We use a dropout layer, and then after the first convolution layer, and then each convolution layer has a batch norm activation and then Gaussian noise regularization. Again, this Gaussian noise was to help prevent overfitting, and we'll talk about that hyperparameter tuning here in a bit. Okay, so model training. Don't mind this figure on the right. This is kind of like something, I have an automatic training plot figure generator, and I was testing something out and it overwrote all of my other ones. But this is kind of an example of what happens. So to do the model training, when you look at the actual data set, there are some underrepresented classes, particularly snow and ice and shadows, and also in some cases water. And when you're training these, and when you're doing your back propagations, your weights that are adjusted can be skewed based on how much training data you have for particular classes. So we use class weighting to make sure those underrepresented classes were actually represented in this back propagation for the parameter updates. And so we use the atom optimizer and DICE plus binary cross entropy loss function. This is shown to have really good accuracy or training results based off of Kaggle. If you're not familiar with Kaggle, that's a online deep learning competition website that I think is a subsidiary of Google, and they have a lot of good examples on deep learning and stuff, and so that's where I plugged that guy from. We used a batch size of 36, and we ran for at max 100 epochs, but we had early stopping after the losses improved for 5 epochs to prevent overfitting. And again, we flipped, rotated, and transformed these images to help give different looks. And then each image, so if you have a particular image, for each epoch, it can be flipped, transformed, and rotated randomly for each epoch. So that way the model is not seeing the same image each time it's running through an epoch. And so we have this GPU cluster on Socrates, which has 4 NVIDIA Tesla T4 GPUs, and that's what we use to train the model. And with this kind of model architecture and this compute, it took about anywhere between 18 to 24 hours to train the model. So it was a lot of compute. Okay, so on top of all this hyperparameter tuning, or on top of all the model architecture, there were some parameters that we can tweak and adjust to help improve accuracies. And again, we also had 2 different model architectures, whether we're using concatenation or addition for the upsampling. And so we use hyperparameter tuning to try and fit those. And we use the Keras Tuner package, which if you haven't used, it's a very, very nice package to do hyperparameter tuning. And here's an example of the outputs. The full documents for hyperparameters are at this link. And so the accuracies and precision and recall kind of vary. And we used actually recall for the testing function, I would say. Basically, so we want to make sure, so recall is error of omission metric. So we're making sure if you have high recall, that means we're not missing classes. And so that's kind of what we're trying to tune for, to make sure every class is. We'd rather mask more pixels than non-pixels if that's the case. Okay, so some results. So the best parameters that we found, so we used the learning rate of 0.01 with the atom optimizer. We had a dropout rate after in each block of 0.5. And then for each convolution layer, we added a Gaussian noise. So this is like standard deviation of the of a normal distribution by 1.4. We actually we tuned different activation functions, so whether we want to use ReLU or ELU, and then the architecture, so LinkNet, so adding was the best. And so, again, you can look at this sheet and see which one provided the best one. And so for the evaluation statistics, so we held off to, I think, 15% of the data to actually evaluate independently of the training data. And so the accuracy was around 95, 96%, which is pretty high. And we're getting a recall of 95%. Which again is really good, especially for a global model. Okay, so just showing some results here. So this is a example in the Amazon, and there's links to this later on. I'll share the slides, but there's a link to this example later on in the slides. But basically, this is over the Amazon where you have some clouds, you have some cloud shadows, a lot of water. And basically, by running this model on Earth Engine, you can predict a nice, clean quality assessment band. And I don't have an example comparing the CF mask, but basically, if you look, it does a pretty good job. If you notice up here with the shadows and over here with the water versus shadows, we'll touch upon that a little later. But overall, it does a really good job. And also, as a nice plus, if you're interested in so this is taking the maximum probability for each pixel, which class it is. But if you want to use your own kind of thresholding and figure out what's going on internally within the model, you can actually output these probabilities, which is fun too. Okay, so some known limitations. Basically, when we're running the hyperparameter tuning, it didn't technically finish. So it ran through about, I don't remember, maybe 6 or so trials. And then after that, it has an out-of-memory error on the cluster. Basically, we're just going to need more compute or figure out a more efficient hyperparameter process to run this, which is fine. So we got some results, but obviously we want to run through as many kind of examples as we can. And so this is a quite large model architecture. I think there's like 45 million parameters that it tunes, and so it's pretty large. And so deploying on AI platform, we needed to specify a larger compute CPU node to run it. Otherwise, it ran out of memory using the default nodes. And we can talk about that a little later. But basically, we can look into a more efficient model for the architecture. So reducing the number of parameters, but keeping the same or improving accuracy is really what would be interesting. There are errors with thin clouds. This is the case especially over water. You kind of see over here there's, it doesn't really look like there's clouds, or right here you almost kind of see like a very wispy cloud, but could go either way. And there's also class confusion between water and shadow in some cases, particularly vegetated water. It kind of thinks that it's shadow. But as you see here, there's water or like this wetland area, and it considers it shadow. So if you're interested in water, that may be a limitation as well. Okay, so next steps, like I mentioned, quality training data is kind of the backbone of all this. So when we were running through this, we did a lot of iterations of exporting the data and trying to figure out, is this enough data? Do we need more? Is it, the best quality data? And so having more quality labeled data for training I think will help, especially with a lot of these edge cases that the model hasn't seen, like those thin clouds or shadow and water areas. And also exploring advanced model architectures. So if you keep up with literature on deep learning, there's this model architecture, this convolution neural network called EfficientNet. It's kind of the standard now. where they're scaling wider versus deeper neural networks architectures to try and provide a better and more, I guess, I don't know how to say it, but basically like a leaner model architecture while keeping up the accuracy. And there's also a new kind of architecture for these UNet-based autoencoders. And so you basically it's a UNet, but along the ways, instead of just skipping over to the upsampling, you have these residual pathways that you are upsampling as well, and then you take the average. I've been playing around with this one and trying to get some code working on this. It's actually quite interesting. But because of all these residual layers, again, it's a quite heavy model in terms of number of parameters. And then lastly, something that I've been interested in is looking into physics-guided neural networks. So a lot of these neural network trainings, it's just based off of the output classes. But in this case, where we are looking at clouds versus water, what have you, there are some physical rules that associate that from the remote sensing kind of theory. And so I would like to be able to basically constrain the model and say like, okay, like you have this, you're saying it could go either clouds or shadows or water, but in remote sensing, this would actually be water, so make sure it's a water kind of thing. And that requires some advanced writing an advanced model class. If you're a super user of TensorFlow, there's multiple ways to write a model. And this would be working with the classes, and then writing a custom model training step where we're actually looking at those physically guided kind of constraints. Okay, yeah, so I know I breezed through a lot of that. I have code sources, so online on the GEE community GitHub organization, I've been posting, I think there's only 2 right now, but I would like to do more, but TensorFlow examples. And so if you click on this link, it will bring you to this notebook, and you can actually open it and run in CodeLab. This should be an end-to-end example where you are taking that SPARCS dataset, sampling it, building your model, training it, and exporting to AI platform and using it in Earth Engine. So this should be an end-to-end workflow. And then another one is this model. So Nick has been very, very kind and is hosting the model for us. So that way we don't have to fit the bill for a lot of these large-scale computations. And so if you click on this link, it should open you up to the a code example where it will load in the model and you can use it for inference. Oops. But if it doesn't work and you get like permissions error, it's probably because you're not part of the severe EETF Google Groups. So we manage the permissions through a Google Groups. And if you would like to use it and you don't have access to it, just email Nick or I. You might get a faster response to me. I don't know, Nick, if I can sign you up to add people to it. But
email Kel.
There you go. Just email me, and Tim has access to it too. So Tim should be able to add people on there, and then we can get you on there. Yeah, there's some references in case you're interested in looking at things, and I'm happy to take any questions. And I'm going to post these slides on here, and I do want to thank Nick for all the support and help and discussion back and forth on this. This was
all Kel. Great job.
Yeah. But yeah, I'm happy to answer any questions, or if you have questions later on, feel free to email me directly.
I have a couple questions, if you don't mind.
Yeah, sure. Shoot.
Do you mind throwing the link to that severe EETF group just in the, or is there a chat on Google, whatever we're in? Meet?
Let me send it in the chat.
Oh, perfect. Thank you. Just because I just got a bunch of training data, so I get to, this is quite pertinent to what I need to do. Very similar problem. I had a couple questions about the model architecture. So you said you were using VGG19 as the decoder, right?
Yes. Or sorry, encoder.
Or excuse me, as the encoder. So this is a question I've had about using pre-trained, I guess, like backbones. VGG, if I remember correctly, is distributed with RGB input, so it's assuming 3 channels. How do you modify a backbone? Do you just add 3 additional channels for Landsat and then, or?
Yeah, that's a good question. And so we didn't use the pre-trained model. So we had to start the model training from scratch. And TensorFlow has awesome, it's a really good library. It has these applications, and so you're able to load in, say, VGG19 or ResNet 50 or whatever, kind of these more, what's the word I'm thinking of? Basically, the more well-known models, you're able to load them in, but you can also specify your input tensor. And so for basically, and this is Jack, right?
Yes. Yeah.
Okay. Yeah. We could follow up later, and I could send some examples. Basically, you specify an input tensor using Keras, and you do that with like you do your normal shape, kind of like we would do like 256 by 256 by 6. It has 6 channels, and basically you use that as input. Maybe I can show an example here.
No, that totally makes sense. I was in a situation where my input, in a sense, has 9 channels because it's multiple 3-band images going in, and I wasn't sure if there was a way that you could maybe just duplicate multiple pre-trained like layers early on, and I couldn't really come up with a good rationalization, but just treating it as a backbone but not with the pre-trained weights and then modifying it a little bit makes sense.
Yeah. I have seen it, though, where someone has basically done a pre-trained weight. I'm trying to find. So, yeah, here's where you do the input tensor, and then you basically say input tensor is in tensor, right there. Okay. But I have seen it where someone does like an input tensor like this, and then on top of that, they do a convolution or do some kind of convolution or sequence of convolutions to get that down to a 3-channel, and then they use it with the pre-trained model weights. Does that make sense? Yeah,
definitely.
So say if we have 6, I would probably do like a convolution, and then maybe a depth-wise convolution, and only output 3 or something like that, and use that as the input. But I haven't really tried it out, and I don't know if that would really work or not.
And then I guess as a non-technical question, well, actually, does anyone else have a question? I don't want to just keep rolling here.
I think it's all you, Jack.
Oh, sweet. All right. How is the performance of this over urban areas? One of the, I guess, kind of a side project I've been working on is trying to track damage in Aleppo, or mapping damage after the conflict in Syria. And we found huge issues using the kind of default quality bands produced by FMAS, just because over urban areas, bright things tend to, you tend to get like commission error like crazy. Did this seem to fix it? Just because we had thrown around this idea of we should just do this sort of thing using Joe's data to see if we can get it to work. Does it seem like it's a lot better over urban areas and this kind of fixes that problem, or?
Yeah, give me 1 second and we can actually try and run something in real time.
Sweet.
Oh, the live demo.
Demo gods.
Yeah, so this is using that script at the end of, so it's using this script here. So if you click on that, it'll load you up to this example in the Amazon, but I'm literally just dragging this over Aleppo and seeing if this will run. I hope it's not something super outrageous.
Oh, that's a pretty. Although this is the type of conditions we see a lot, where you get kind of the clouds above the city because of the heat from the heat island.
Yeah.
So part of the issue, it's a challenge, is just because there's a lot of clouds. But
yeah. Okay, well, let's let that cook for a bit and see if see what happens. Oh, we're getting some results. Okay, so yeah, so I'll leave that up and see if it runs, and we can touch base here in a couple minutes. Does anybody else have a question?
Hi, Cal. Farouk here. Great work. Just have a question about your inquiry into the physics-based neural nets, because you are using, you are physically constraining the neural net through your data sets used for training, coming from the CCAVP and the SPARCS data set. So I'd be interested in working out the additional constraints that can be done through index-based indices, etc. Because you also have to be careful about the physical constraints for classifying clouds and other types of objects in this before. That's something that I just wanted to inquire on how you're planning to do.
Yeah, that's a really good question, and I haven't really put too much thought into it. One thing that comes into mind is doing a quick data-driven approach, like doing like a decision tree or multiple decision trees and seeing what happens, but I'm not sure. But yeah, I mean, when I do get to it, I'm happy to include whoever wants to be involved.
Yeah, because the physical sort of algorithms have been applied. That whole decision tree making process from the reflectances have been already applied. But how additionally can we constrain it? That's we don't want to double count, and of course include new constraints if possible.
Yeah. No, I'm with you.
Yeah.
And so, Jack, it looks like this does a decent job, but is missing some shadows.
that's a lot better than we tend to see with the default. The shadows are always kind of, because the city in the end has shadows, so it's always kind of a problem. So if it just gets the clouds, that'd be so awesome.
Yeah, and I mean, this is open for everyone. And again, this link, I think we need to add you to the severe EETF group, but basically it's just loading in the model like normal. And thanks again, Nick, for hosting this. It's a huge help. So.
Yeah, and let me just add, the more people that hit this thing, the better. A, because we want to know whether it works in different contexts, and B, because if the served model gets overloaded, then we can put it on a different machine.
Hey, Cal, this is Tim. A great presentation. Thanks so much. I'm sorry, I feel like we gave you too short amount of time to get through all this material, so I apologize. And thanks everybody for sticking on the line, because this is a great conversation. Jack, I just added you to the TensorFlow group, so you should be able to be involved in that now. And then the question I had to Cal is, as you're going through the presentation, you talked about like the encoders and decoders. You mentioned that you're doing a dropout on the encoding. Are you also doing that on the decoding portion as well?
Yeah, that's a good question, Tim. And it's actually flipped. So I was doing dropouts on the decoding, but not the encoding. So the VGG 19 model I left as is. And that's a pretty vanilla encoder where it's doing like convolution, convolution, max pool, convolution, convolution, max pool. There's no like batch norm. There's no activations along with it as well. So it's pretty vanilla. But no, I didn't touch the encoder, but the decoder does have those dropouts for each block, and it's one dropout per block. It's not like after each convolution there's a dropout.
Yeah, thanks. I know that was like a big source of discussion a year ago of like what is the rules of thumbs that we should be applying in this situation, and yeah, it seems like it's using something sort of out of the box. That BGG 19 is a really great place to start, and I want to pick your brain more, and we'll definitely tee this discussion up on one of your sessions at the exchange about like answering research questions and how to parameterize, and maybe not go too far down the well and just get to the answer too. So, and then I had one more point I just wanted to say. I'm happy to see that the Socrates GPU space is being utilized, and I don't know if you've got a pathway forward for us as a group to tap into that, but it's cool to see that you're utilizing it as well.
Yeah. So on the severe GPU cluster, I will say that it's been on my plate to kind of dig more into it. So I've been working with Jeff to kind of like get this set up and use it. And this started a couple months ago, but ultimately the way we see it being used from my perspective and the GIT perspective is that we are able, or we should theoretically be able to provision VMs on that GPU cluster with different levels of CUDA nodes or different level of memory or what have you, right? And so theoretically, if someone wants to, sorry, Nick, not taken away from GCP, but if the severe network would like to, spin up like a 8 gigabyte VM for doing a quick training or something, we should be able to do that, and we should have multiple people being able to run. We should be able to provision a GPU out multiple times, and or give people like say 2 GPUs or what have you, right? Depending on application. So there's a lot of ways to cut it, but we haven't really gone into that yet. Yeah, coming soon.
Yeah, thanks, Kel. I know you've been working hard on that. It's great because that was one of the main issues when we first started talking about the impervious surface work from Mekong over to HKH, and like dealing with what Tanuja had brought up of how to get more comfortable with cloud computing and not necessarily running up a big bill. And this could be a good stepping path to getting to that point. So thanks and kudos for digging into that. Are there any other questions on the line?
Yeah, I would say too, if if you have a question later on, feel free to email me directly, and I'd be happy to help answer any questions. Or if you want to go back and forth on models or something, let me know.